Okay, hello and welcome everybody to today's ISGC seminar talk. It's my very big pleasure to introduce Elizabeth Winstanley. She did her doctor in philosophy, Dr. Phil, sorry, in 1996 at Oxford University. And since in 2000, she got a lecturer position at the University at Sheffield. And since 2009, she's a professor of mathematical physics at the same place. And she will talk to us about quantum states on black hole spacetimes. Thank you very much for giving this talk. For the questions, please feel free to drop them in the chat or simply raise your hand, and then I will find an appropriate time to interrupt you. And with that, I hand over to you. Thank you very much for giving the talk. The stage is yours.
Well, thank you very much indeed, Torben, and thank you for the invitation, and a particular thanks to those of you for whom this is either pretty early in the morning or pretty late at night. It's great to be here with you today. I'm very fortunate being in the UK because I'm kind of in the middle. So I'd like to talk about some work which has been done with Visakam Balakumar, who's now finished his PhD. He was here in Sheffield. Rafael Bernard is at the University of Para in Belém in Brazil. And I'll also briefly mention some work that's currently in progress with Cormac Breen, who is in Dublin Technical University. George Montagnon is a PhD student here in Sheffield, and Peter Taylor is in Dublin City University. And I assume that everybody can hear me okay, otherwise somebody would have put something in the chat by now. Excellent. So this is going to be a talk about quantum field theory in curved space-time. And this is a semi-classical approach to quantum gravity, where we regard our space-time as entirely classical and fixed, and we study the propagation of a quantum field on this fixed background. Now, this is a very long-standing area of research, and one of the most famous results from this framework is the discovery by Hawking that if you have a black hole formed by gravitational collapse, for example, of a dying star, then at late times, far from the black hole, there will be an outgoing flux of quantum radiation. And furthermore, that radiation is thermal in nature. So black holes have a temperature, the Hawking temperature, and that's proportional to a quantity kappa, the surface gravity of the black hole. This is a measure of the strength of the gravitational field at the event horizon of the black hole. So my focus in this talk is going to be how we define quantum states on black hole spacetimes. And I'm going to do that using canonical quantization. So let me just schematically outline the procedure, and let's consider the simplest type of quantum field, a neutral scalar field. We start by considering an orthonormal basis of mode solutions of the field equation, so the Klein-Gordon equation. And here I've written this mode solution schematically in terms of some index J. Now, what I've done here is I've split these field modes into two types that I've denoted phi plus and phi minus. Now, the phi plus modes are going to be positive frequency modes. So what do I mean by that? Well, suppose that we're just in 1+1 dimensional Minkowski space, and we therefore have plane wave solutions of the field equation. So, and the plus and minus are left and right moving. So omega here is a constant in my plane wave, that's the frequency, and I will say that these modes are positive frequency if little omega here in the plane wave is positive. And similarly, I will define negative frequency modes, phi minus, as being those modes for which little omega is a negative quantity. So having made this classical expansion, I'm then quantized the field by promoting the expansion coefficients that I've called AJ and AJ dagger to operators. And these operators will satisfy the usual commutation relations for a bosonic field. And from these commutation relations, I interpret the AJ hat, the coefficients of the positive frequency modes, as particle annihilation operators, and the AJ daggers, the coefficients of the negative frequency modes, will be particle creation operators. And once I have my particle annihilation and creation operators, I then define the vacuum state as that state which is annihilated by the particle annihilation operators. So if we just track back on this slide, our definition of a vacuum state depends on how we define our particle annihilation operators. And how we define our particle annihilation operators depends on how I split my modes into positive and negative frequencies. And in turn, that depends on the frequency comes from the term in the plane wave solutions that's proportional to the time. So now I want to apply this general approach to black hole spacetimes. And let's start with the simplest possible black hole, a Schwarzschild black hole in static and spherically symmetric coordinates. So r, theta, and phi are the usual spherical polars. T is the time. I'm going to call that the Schwarzschild time. And m here is the mass of the black hole. So if we're going to do canonical quantization, I need to start with a basis of field modes. And let's just consider a massless neutral scalar field for simplicity. So the Klein-Gordon equation is separable on the Schwarzschild metric, and this is the form that the mode solutions take. So let's have a look at the various bits that we've got here. We have a spherically symmetric metric, so the angular part of my mode is given by a spherical harmonic. We don't need to worry too much about these. Little m here is the azimuthal quantum number, and L is the total angular momentum quantum number. We have a normalization constant because I need my modes to be orthonormal. Again, we don't need to worry about the details of this for today. I've got a time periodic part, and omega here is going to be the frequency, and it's the frequency with respect to Schwarzschild time t, the time coordinate that I have in the original metric. So a natural definition of positive frequency with respect to the Schwarzschild time is to take omega positive. And the last part of the metric is the radial function. And at various points in this talk, we're going to have to look at the radial function in some detail. Now, if we make a change of coordinates, then the radial function satisfies a Schrödinger-like equation in one dimension. So our star here is a coordinate called the tortoise coordinate. It goes to -infinity as r goes to 2m and we approach the event horizon of the black hole. And r star goes to +infinity as little r goes to infinity as we go far from the black hole. And in these two asymptotic regions, in general, the form of the potential is quite complicated, but it simplifies in the asymptotic regions close to the event horizon and far from the black hole. And there, for a Schwarzschild black hole, the potential simply goes to omega squared, the square of the frequency. So that means that in these two asymptotic regions, I'm just going to have plane wave solutions of the field equation. So I can now construct an orthonormal basis of field modes, and these are going to be the in and up modes. So here I've drawn a diagram. It's a conformal diagram of the region between the event horizon, so future and past event horizons, and future and past null infinity. So time is going up from the bottom of my diagram. So I define my in modes as being ingoing from infinity. And I've got a one-dimensional scattering problem. So part of my ingoing wave is reflected by the potential in that one-dimensional Schrodinger equation and is reflected back to infinity. And the coefficient of my reflected wave is always going to be A. And part of the wave will be transmitted through the potential barrier and will go down the event horizon of the black hole. And the amplitude of the reflected part is always going to be B. So those are the in modes. The up modes, in contrast, start as outgoing close to the event horizon of the black hole. Part of the wave is reflected back down the horizon. The coefficient in the reflected part, again, is A. And part of the wave is transmitted to infinity, and the transmitted part has a coefficient B. So these modes, these two sets of modes, form a orthonormal basis, and we can therefore use them in our canonical quantization procedure to define states. And there are three such states on a Schwarzschild black hole which have been widely considered in the literature. So the first is the Boulware state, which I'll denote B. And this is defined by taking positive frequency to mean positive frequency with respect to the Schwarzschild time that we had in the original metric. And the resulting state is the Boulware vacuum. Now, in this talk, I'm going to be defining a lot of states and I want to compare them. And I'm going to compare their properties by considering unrenormalized expectation values. So here's an example, and let me talk you through how to read these. So this is going to be an unrenormalized expectation value of an operator O hat in the Boulware state B. And I've written this as a sum of the contributions from the various modes. So I've got a sum over the angular quantum numbers M and L. I have an integral over frequency, so positive frequency omega. And then here I've got the individual contributions from each of the in and the up modes. So what little o is, so for example, suppose big O was the stress energy tensor operator. Then little o would be the classical stress energy tensor for that particular field mode. So it's the classical contribution from each of the modes. And the way I interpret this particular mode sum is that the state B has no particles in either the in or the up modes. Okay. Now, this Schwarzschild time coordinate that I use to define the Boulware state is a good coordinate outside the event horizon of the black hole, but it fails to be a good coordinate on the event horizon of the black hole. So we could alternatively take positive frequency to mean positive frequency with respect to Kruskal time, a time coordinate that's regular across the event horizon of the black hole. And if you take that definition of positive frequency and go through your canonical quantization procedure, you end up with the Hartle-Hawking state that I'll denote H. So what does this look like? Well, here are the unrenormalized expectation values in this case. So I have contributions again from the in and the up modes, but I now have this Koth factor as well. And this Koth factor is a thermal factor. It depends on the Hawking temperature TH of the black hole. And the other key thing to notice is that it involves inside the thermal factor, I have omega, the frequency of the modes. So this state has a thermal distribution of particles in both the in and the up modes. Now, for both the Boulware and the Hartle-Hawking state, we treat the in and the up modes equally and the same footing. We can also consider a third state, the Unruh state. And here we take the in modes to be positive frequency with respect to Schwarzschild time. So the Unruh state has no particles in the in modes, but we treat the up modes as having positive frequency with respect to Schwarzschild time. So we have a thermal distribution of particles in the up modes. So that's how the states are defined. What are their properties? Well, the Boulware state is a state which is as empty as possible at infinity. This makes sense because I've defined it using a time coordinate, which is a good time coordinate far from the black hole. And just as Schwarzschild time fails to be a good time coordinate on the event horizon, the Boulware state diverges on the event horizon of the black hole. The Hartle-Hawking state, in contrast, because it's defined using Schwarzschild time, is regular on and outside the event horizon. And this represents a black hole in thermal equilibrium with a heat bath at the Hawking temperature. The Unruh state is not an equilibrium state. It has this outgoing flux of Hawking radiation in those up modes. And one of the nice things about the Unruh state is that it's regular on the future event horizon of the black hole. We will need that towards the end of the talk. So I'm going to have a slurp of tea. Are there any questions on that point? Okay, so we've defined these standard quantum states on a Schwarzschild black hole. So the question then is, well, can we do this on other black hole spacetimes? So what about if we consider a rotating Kerr black hole? So this is the metric. You'll be pleased to know you don't need to remember the details. The take-home message from this is that the metric is more complicated. It depends on the mass m of the black hole, and a here is a parameter governing the speed with which the black hole is spinning. And I guess the other take-home message is that the metric is no longer spherically symmetric. So we'd like to define Boulware, Unruh and Hartle-Hawking state on a Kerr black hole. However, there's a bit of a problem in that there is a theorem by Kay and Wald that there is no Hartle-Hawking state for a neutral quantum scalar field on a Kerr black hole. So what does that mean? Well, it means that there's no state that has these two key properties of a Hartle-Hawking state that's a thermal equilibrium state and that's regular on and outside the event horizon of the black hole. So one question is then, well, what goes wrong with that canonical quantization procedure? Why doesn't that work? And in order to answer that, we need to drill down into our scalar field modes. So again, I'm considering a massless neutral scalar field. The wave equation is again separable. Because I no longer have a spherically symmetric black hole, instead of spherical harmonics, I now have spheroidal harmonics. We do not need to worry about these. What we do need to look at in some detail is the radial part of my mode. And just as in Schwarzschild, this radial function satisfies a one-dimensional Schrödinger equation in terms of the tortoise coordinate. The definition of the tortoise coordinate is slightly different, but it has the same properties as in the Schwarzschild case. So let's have a look at the form of the potential in our Schrödinger equation in the two asymptotic regions. So first of all, let's have a look at what happens when R star goes to infinity. That corresponds to R going infinity to infinity. We're far from the black hole. And in that case, just as in Schwarzschild, the potential tends to omega squared, which is the constant that I have in the time part of my scalar field mode. So the frequency of my mode far from the black hole is going to be omega, just as in Schwarzschild. However, near the event horizon, as our star goes to -infinity, the frequency isn't omega, it's this shifted frequency, it's omega tilde, where omega tilde is omega minus, so little m is the azimuthal quantum number, and big omega h is the angular speed with which the black hole is rotating. So because of the rotation of the black hole, the frequency near the horizon gets shifted. So that means that the form of the modes is going to be a bit more complicated in this case. So let's have a look, first of all, at the form of the in modes. So I have plane wave solutions far from the black hole and close to the horizon. But notice that while the frequency of the modes at infinity, as our star goes to infinity, is omega, near the horizon, I've got this shifted frequency omega tilde. Now, Rn is a solution of a one-dimensional Schrödinger equation. I've got a scattering problem like we meet in quantum mechanics courses. So this means that I can derive a relationship between the amplitudes of the reflected and the transmitted parts of my field mode. And this is the equation that you get. And it involves the frequency at infinity, omega, and the frequency at the horizon, omega tilde. And you can see that if it's possible for omega and omega tilde to have the opposite sign, then the magnitude, the amplitude of the reflected part of my wave will be bigger than the amplitude of the incident part of my wave. And this is a classical phenomenon known as superradiance. So what's happening is that this particular subset of modes is extracting rotational energy from the black hole. And it only happens for modes where omega and omega tilde have opposite signs. So we scatter a wave and we get more wave out than we send in. Now, these modes play an important part in the process of canonical quantization, and they'll crop up again later. So the in and the up modes still form an orthonormal basis. Because our in modes start from near infinity, the natural frequency for the in modes is the frequency at infinity, omega. Whereas for the up modes, because these start close to the horizon, their natural frequency is this shifted frequency, omega tilde. Now you can see from these two expressions for omega and omega tilde that it's possible for omega and omega tilde to have different signs. So if little omega is positive, but less than m omega h, omega tilde will be negative. So this is what complicates the quantization on a Kerr background. Now, the K-Wald theorem tells us that there's no Hartle-Hawking state on Kerr. There's no state which is a thermal equilibrium state, regular everywhere on and outside the event horizon of the black hole. So what's the closest that we can do? And there are two Hartle-Hawking-like states that have been considered in the literature. The first is the CCH state due to Candelas, Krasnowski, and Howard. And I think the easiest way to understand this is by looking at these unrenormalized expectation values. So the CCH state has a thermal factor, a Koth factor in both the in and the up modes. Both involve the Hawking temperature TH. But while the up modes involve omega tilde, the natural frequency for the up modes, the thermal factor for the in modes involves omega, the natural frequency for the in modes. So the modes are thermalized with respect to their natural frequencies. So what are the properties of this state? Well, it's certainly regular outside the event horizon. It has good regularity properties. However, it's not a thermal equilibrium state, and we can see that from these unrenormalized expectation values because we treat the in modes differently from the up modes. So CCH is regular, but not an equilibrium state. The second state that's considered in the literature, I'm going to call the FT state. This is due to Frolov and Thorne. And here, this is a good test. This is a bit like spot the difference. So I've now got omega tilde in all the thermal factors. So in the thermal factors for both the in and the up modes. So what are the properties of this state? Well, this is an equilibrium state. I've got the same thermal factor for all modes. However, it is rather horribly divergent, and it's divergent everywhere except possibly on the axis of rotation. So we can see now that why there's no Hartle-Hawking state. We either have an equilibrium state that's divergent, or we have a regular state that's not an equilibrium state. Now, one of the complications of doing quantum field theory on Kerr is because the metric is complicated and there's less symmetry, the mathematical details are more complicated. So for the rest of this talk, I'm going to go back to considering a static and spherically symmetric black hole. But before I go into that, I think I'm going to have another slurp of tea and just see if there are any questions at this point.
I have one question. So what do you mean by potentially an equilibrium state?
Ah, that's a very good question. So potentially in the sense that if it was well behaved, it would be a thermal equilibrium state. But it's so divergent that I'm not really sure you could call it an equilibrium state.
Oh, okay.
Because any expectation value is just going to blow up basically virtually everywhere.
Mm-hmm. Thank you.
Okay.
Can I ask a live question about what your definition about the regular? What do you mean, the regular?
Ah, very good. So technically, I mean Hadamard, if you know what that means. I guess what I mean is that expectation values of observables are finite from a physical point of view. So if I calculate the stress energy tensor, expectation value, then I will get finite answers. Does that answer your question?
Yes, thanks. So only all kinds of observables, I mean the expectation value of it has to be finite, right?
Yeah, absolutely.
Okay, thanks.
Okay.
Thanks.
Okay, fabulous. Okay, so for the rest of this talk, I'm going to consider a Reissner-Nordstrom black hole having mass m and charge capital Q. And I have, as well as a background gravitational field, I have a background electrostatic potential depending on the charge of the black hole. Now I'm going to keep the electrostatic potential as fixed and classical. And the only quantum field that I'm going to consider is a quantum charged scalar field. So this is the scalar field equation. Little q is the charge of the scalar field. And I've also introduced a scalar field mass that I've called mu. Okay. So we know from our consideration on Schwarzschild and on Kerr that we need to look at the field modes. And we've also been comparing states by looking at unrenormalized expectation values of observables. Now, so far, I've written those in a kind of abstract way. I want to now actually be explicit about the observables that I'm going to consider. So the simplest observable is the scalar condensate. This is basically the square of the quantum field. HC is Hermitian conjugate. And the scalar condensate doesn't involve any derivatives acting on the scalar field. I can also consider the current. This involves one derivative acting on the scalar field. And I'm also going to be interested in the stress energy tensor operator. I've not written this out. This involves two derivatives acting on the scalar field. Now, I'm not going to worry about all the components of the current and the stress energy tensor. I'm just going to focus on two. And these are going to be the components that involve fluxes. So the radial component of the current depends on the flux of charge from the black hole that I'll call K. And the RT component of the stress energy tensor involves the flux of energy, curly L. So while all the states I'm considering are static states, it's still possible to have a static flux of particles of charge and of energy. And when I say equilibrium state, what I mean is that the fluxes of charge and energy are zero in that particular state. So there's no net ingoing or outgoing flux. Okay, so now let's look at the scalar field modes. So we're back to a spherically symmetric black hole. So we're back to spherical harmonics. We know from Kerr that we need to pay close attention to the radial function, which again satisfies a one-dimensional Schrödinger equation. The definition of the tortoise coordinate is slightly modified because the metric has been modified. But again, R star goes to -infinity near the event horizon and goes to +infinity at infinity far from the black hole. And we also know from Kerr that the key features are how does the potential behave in these two asymptotic regions. So first of all, as R star goes to -infinity, as we approach the event horizon of the black hole, we have a shifted frequency. Now, I've called this omega tilde. It's not the same omega tilde as in Kerr, but it plays the same role. So I hope that won't be too confusing. So omega tilde is omega, the quantity in the time part of the mode. Whoops. And there's a shift, and that shift now depends on the electrostatic potential at the event horizon. So it depends on the scalar field and the black hole charge, and R+ is the event horizon radius. Now, far from the black hole at infinity, again, it's a little bit more complicated. So I've got omega squared, but I also have minus mu squared. So mu is the mass of the scalar field. So the form of the potential depends on the frequency and on the mass of the scalar field. So let's have a look at the solutions of the radial equation in just a little bit more detail. Now, as R star goes to -infinity at the event horizon of the black hole, it's straightforward. We have the usual plane wave solutions with this shifted frequency omega tilde. So A and B here are just constants. As R star goes to +infinity, it's a little bit more complicated because the form of the solutions depends on whether little omega squared is bigger than or smaller than mu squared. So if little omega squared is bigger than mu squared, then we have the usual plane wave solutions. But now I've got a big omega in there, which is a correction due to the mass of the scalar field. I'm sorry for all the omegas. If, on the other hand, mu squared is bigger than omega squared, then we don't get oscillating solutions. We get exponentially decaying and growing solutions. So in this case, so C and D are again just constants. In this case, I'm going to ignore the exponentially growing solutions because I need orthonormal modes. So I need to be able to normalize the modes. So I need the modes that are exponentially decaying. Okay, so that's the solution of the radial equation. Now let's have a look at our in modes. So this is the form of the in mode. So I have plane waves both near the horizon and at infinity. And this is just to remind you of the definitions of big omega and of omega tilde. The radial function satisfies a one-dimensional Schrödinger equation. So I can derive an equation for the amplitudes of the reflected and the transmitted parts of the wave. And that equation depends on the big omega, the quantity at infinity, and on the shifted frequency omega tilde near the horizon. And you can see that just as in the Kerr case, if it's possible for big omega and omega tilde to have opposite signs, then the amplitude of the reflected part of the wave will be larger than the amplitude of the incident part of the wave. And again, we have superradiance. So in this case, this is superradiance caused by the charge of the black hole. So my charge scalar wave is extracting charge, electrostatic energy from the black hole. Now, this can only happen if we have modes for which big omega and omega tilde have the opposite sign. And by looking at these definitions, you can see that this is not possible if the mass of the scalar field is larger than the magnitude of the electrostatic potential on the horizon. So for sufficiently large mass, we don't have superradiance, and big omega and omega tilde must always have the same sign. So that's the in modes. What happens with the up modes? Well, what happens with the up modes depends on whether little omega squared is bigger than or less than mu squared, the mass of the scalar field. So in the case where little omega squared is bigger than mu squared, we have plane wave solutions both near the horizon and at infinity, just as we've had previously for our up modes. However, if mu squared is bigger than omega squared, then near infinity, we have an exponentially decaying mode rather than a wave-like mode. So what's happening here is that because the frequency is low, the energy of the wave isn't big enough to tunnel through the potential barrier. So effectively, we've got no transmitted part of the wave in this case. But I can still treat both of these as up modes. And these up modes, together with the in modes, form an orthonormal basis. Now, because the in modes start from near infinity, their natural frequency is this big omega, the quantity, the frequency at infinity. Whereas the up modes, because they originate near the event horizon, their natural frequency is the shifted frequency omega tilde, the natural frequency near the horizon. Now, in this case, I've put some dots in here because for some of the up modes, we don't have this transmitted part of the wave. So the situation's a bit more complicated. And part of the complication is on whether, even though we've got these two frequencies, whether big omega and omega tilde can have opposite signs, or whether they always have the same sign. Now, it's simpler if we're in the case where there's no superradiance. So although big omega and omega tilde are different, they always have the same sign. And in this case, I can define a Boulware state B in exactly the same way as I do on Schwarzschild. I simply say positive frequency means positive frequency with respect to Schwarzschild time t. Here's the Unruh normalized expectation values. This is a state that has no particles in either the in or the up modes. And it's an equilibrium state. It's as empty as possible at infinity. There is no flux of either energy or charge from the black hole. We can also define a Hartle-Hawking state by taking positive frequency to mean positive frequency with respect to Kruskal time. And in this case, I have a thermal distribution of particles in both the in and the up modes. They have the same thermal factor. It involves omega tilde, the natural frequency near the horizon. And this is, again, an equilibrium state. It's a thermal equilibrium state. There's no flux of either charge or energy from the black hole. So even though we're dealing with a charged scalar field, when there's no superradiance, the quantization procedure follows through in a straightforward way, just as it does on Schwarzschild. So the question then is, well, what's going to happen when we have superradiance? In order to explain that, I need to have some more tea and pause to see if there are any questions. Okay, so on the previous slide, I defined Boulware and Hartle-Hawking states. I didn't yet define the Unruh state. Now, the advantage of the Unruh state is that we treat the in and the up modes differently anyway. So the fact that we've got different natural frequencies for the in and the up modes doesn't cause us any problems. So here are the unrenormalized expectation values for the Unruh state in the case where we have superradiance, and also equally in the case where we don't have superradiance. So in the in modes, we have no particles in the in modes. Now, because we're getting quite a lot of omegas, from now on, I'm going to take the mass of the scalar field to be 0. So big omega is just little omega, and we do have superradiance. So we still have no particles in the in modes. In the up modes, we have a thermal distribution of particles at the Hawking temperature, and the thermal factor involves omega tilde, this shifted frequency. Now, this is not an equilibrium state. There are non-zero fluxes of both charge and energy in this state, and that comes from these up modes. Now, the actual expressions for these fluxes are a bit complicated, but the key features are that notice that I have a Planck distribution. And inside my Planck factor, I have omega tilde, or I have this shifted frequency. And it's a bit like having thermal radiation with a chemical potential. So this is the contribution from the positive frequency modes. For the negative frequency modes, again, we have a Planck factor, but the sign of the chemical potential changes. And this is completely standard. These results here, these aren't new. These were found by Gibbons back in the 1970s. I just didn't have room to put the reference on the slide. And the Unruh state is going to be regular on the future horizon of the black hole. So the Unruh state is uncontroversial, even when we have superradiance. What about a Boulware state? So we'd like to define the Boulware state by saying positive frequency means positive frequency with respect to the Schwarzschild time t that appears in the Reissner-Nordstrom metric. So this means I take omega positive for the in modes, the natural frequency at infinity, and omega tilde positive for the up modes, the natural frequency for the up modes. The state that results from this, I'm going to call B1. And this is what the unrenormalized expectation values look like in this case. So I have no particles in either the in or the up modes. However, this is not an equilibrium state. There are non-zero fluxes of energy and charge. But these non-zero fluxes come from a small subset of modes. They come just from the up modes that lie within the superradiant regime. So in this B1 state, we have spontaneous quantum emission in precisely those modes that exhibit classical superradiance. So this is the quantum version of superradiance. So in particular, this state B1 is not as empty as possible at infinity. So can we define a state which is as empty as possible at infinity. So let's have another go. I'm going to define a state B. Now, this is the Unruh normalized expectation value that I had in the state B1 on the previous slide. And that had a non-zero flux in the superradiant up modes. So what I'm going to do is I'm going to reverse the sign of the contribution from the superradiant up modes. And I can do that by taking twice that off. Okay. So this is the Unruh normalized expectation value in this B state. So what are the properties of this state? Well, this is an equilibrium state. There are no fluxes of charge or energy from the black hole. And it is the state which is as empty as possible at infinity. So this is the analog of the Boulware state on Schwarzschild, but for a charge scalar on Reissner-Nordstrom. And to construct this, we've had to do this unusual treatment of the superradiant up modes. So we've done Unruh, we've done Boulware. I've got a few slides left and a bit of time. So let's have a look at Hartle-Hawking. Now, our experience on Kerr suggests that this is going to be tricky. So let's start by thinking about the analogues of the two states that we had on Kerr some time ago. So the first state I'm going to define, I'm going to call H1. And this is going to be the analog of the CCH state on Kerr. So I'm just going to write down the Unruh normalized expectation values. So here I have a thermal factor for both the in and the up modes, Hawking temperature, but I have thermalized the modes with respect to their natural frequencies. So that means omega for the in modes, the frequency at infinity, and omega tilde, the shifted frequency, the frequency at the horizon for the up modes. What are the properties of this state? Well, it's not an equilibrium state. There are non-zero fluxes. Now, if we look at this term that I have involving the up modes, this is exactly the same as we have in the Unruh state. So the flux coming from the up modes is exactly the same as in the Unruh state. And I've got an additional flux coming from the in modes. So the form is complicated. The key take-home message is that the key feature is that I've got this Planck factor, and that involves the frequency omega, the natural frequency of the in modes. So this is not an equilibrium state. Is it well behaved? Now, I'm not going to consider renormalized expectation values. Renormalization is a very difficult problem. So instead, I'm going to consider differences in renormalized expectation values because these don't require renormalization. Okay. So if I consider the difference in expectation value between H1 and Unruh, this doesn't require renormalization. So let's just consider the scalar condensate. And if you like, I'm using the state U as a reference state because I know that this is going to be regular on the future horizon of the black hole. So this is a plot of this difference in scalar condensate expectation values. I've got the event horizon radius on the left of the plot, and I'm moving away from the black hole as I go from left to right. And the different curves correspond to different values of the charge of the scalar field. I've fixed the black hole charge. Now, these are numerical results. I'm not claiming that this is a proof, but the take-home message from this is that these appear to be well behaved everywhere outside the event horizon of the black hole. So it looks like the state H1 is regular, as we were discussing previously. Okay, so H1 is not an equilibrium state, but it seems to be well behaved. What about the analog of the FT state that we had on Kerr? So I'm going to call that the state H2. So here I have a thermal factor for both the in and the up modes, but I now have the same thermal factor for both modes. So both involve omega tilde now. the natural frequency at the horizon. So perhaps surprisingly, this is not an equilibrium state. So there is a non-zero flux of charge and energy from the black hole. But this comes from a subset of modes. It just comes from the in modes that lie in the superradiant regime. So in this case, for this state, we've got fluxes from the superradiant in modes. So they are not in equilibrium. What about regularity? Well, let's have a look at the difference in expectation value for the scalar condensate. So this is the form that it takes. It involves an integral. And I've got a fraction in my integrand. And you can see that the denominator of my fraction is going to be 0 when omega tilde is 0. The numerator doesn't vanish when omega tilde is 0. So I've got a singular integrand. And furthermore, because of these absolute values here, it is a non-integrable singularity. So this quantity is horribly divergent, and it's divergent everywhere. So this state H2 isn't an equilibrium state, and it's not a regular state. So can we do better? I've got a couple of slides left. So I'm going to define a third state, H. So what I've got here is the unrenormalized expectation value in the H2 state, the one from the previous slide. And that had a flux in the superradiant in modes. So I'm going to do the same trick as I did for the Boulware state. I'm going to reverse the sign of the contribution from the superradiant in modes, and I'm going to do that by taking it twice it off. And I'm going to call the resulting state H. This is an equilibrium state. The flux of energy and charge are 0. What about regularity? Well, again, let's have a look at this difference in expectation values of the scalar condensate. So again, I have an integral. I've written it as the sum of two terms. And the denominators in each of these fractions can vanish, and the numerators don't vanish. However, these are now round brackets, they're not absolute values. And although the integrand is singular, it's an integrable singularity. The Cauchy principal value of these integrals does exist. So this quantity is regular. And to give you some further evidence, again, these are numerics. This is not a proof. But again, this is this difference in expectation values of the scalar condensate. And this seems to be perfectly well behaved everywhere outside the event horizon of the black hole. And since we know that the Unruh state U is a regular, is a well-behaved state, we deduce that the state H is as well. So to wrap up, we've been considering the construction of quantum states on black hole spacetimes using canonical quantization. And in the simplest case, a neutral scalar field on Schwarzschild, there are 3 standard states that are considered. The Unruh state, which has an outgoing flux of particles due to the Hawking radiation. The Boulware state, which is as empty as possible at infinity. And the Hartle-Hawking state, a thermal equilibrium state, regular on and outside the event horizon. In the second half of the talk, I've been considering a charged scalar field on a charged Reissner-Nordstrom black hole. And we've seen that if the mass of this charged scalar field is sufficiently large, then there is no charged superradiance. And the canonical quantization approach goes through in exactly the same way as it does in the Schwarzschild black hole. And we have the Unruh, the Boulware, and the Hartle-Hawking states that have very similar properties to those on a Schwarzschild black hole. In the other parts of the talk, we've been considering the case where we do have classical superradiance. And we've looked at 2 scenarios. The first is where we have a neutral scalar field on a rotating Kerr black hole. And in this case, the K-Wald theorem tells us that there is no Hartle-Hawking state. There are two states that are considered in the literature. The CCH state is well behaved, but is not a thermal equilibrium state. The FT state is a thermal equilibrium state, or potentially, but is rather divergent. And we've looked at how we can define analogues of these states for our charged scalar field on Reissner-Nordstrom. For the Boulware state, when we have superradiance, our first attempt at defining a state, B1, had a flux of particles in the superradiant modes. But we were able to define a new proposed state B, which is as empty as possible at infinity. In terms of Hartle-Hawking-like states, our first state, H1, was regular, but not an equilibrium state. Our second attempt, H2, was not an equilibrium state and was very divergent. And our new state, our third attempt, third time lucky, we defined an equilibrium state that was also regular. Now, throughout this talk, I've been looking at unrenormalized expectation values, and work in progress is looking at the renormalized expectation values, which are what we need to consider in order to really study the regularity of the states. So I'll leave that there. Thank you very much.
Thank you very much for this really nice talk, Elizabeth. Are there any questions?
So may I ask a questions?
Sure.
So I have a question on the exponentially damping solution. And that is a bound state solution for Schrödinger equation.
Yes.
Therefore, small omega should be determined by the condition exponentially increasing solution vanishes.
Yes.
So what is the physical meaning of this bound state solution? You have some physical picture on this state, in this solution?
So they're definitely there. They need to be included in the quantization. So, and these are up modes. So these would be, if we think about, for example, Hawking radiation. So these would be particles created by the black hole in Hawking radiation, but they haven't got enough energy to tunnel all the way out to infinity. So they just get reflected back down the black hole.
Okay.
But that makes sense.
Only some specific small omega, right?
It's only for low energy modes. Yeah.
Thank you.
Okay, you're welcome.
Yeah, any further questions?
Can I ask one?
Yeah.
So,
sure.
So you found that in the charged Reissner-Nordstrom case, and if you have sufficiently large mass of the scalar field, the mass such that the mass can suppress the classical superradiance, you can still define Hartle-Hawking states, right?
Yeah.
So my question is that if you consider Kerr and you add also a mass to the scalar field such that it suppresses the classical superradiance, can we define the Hartle-Hawking states?
So that's a very, very good question. There's a complication on Kerr, which is that if you introduce a mass to the scalar field, you can induce a classical instability. So the quantization of a massive scalar field is further complicated by these instabilities. Now, to be honest, I don't know off the top of my head whether there is a sweet spot where you've got no superradiance and you don't have a classical instability. It's possible that there is. The instability tends to happen for small masses. So I guess I would expect the simple answer to your question to be yes. I'm not sure if anybody has actually gone through the construction in the literature. I'm not aware of anything. I could be wrong. And if anybody knows of a paper where people do this, that would be really useful to know. But you've got to be careful with classical instabilities as well. And you don't have to worry about that on Reissner-Nordstrom.
Okay, yeah. It looks like the proof of Klein walls is more, it's really a no-go. It's more robust than we expect.
It is a robust result. It is only for a massless field. The K-wall theorem is only for a massless field.
Okay.
Yep. Yep.
Okay. Thank you.
You're welcome.
Are there any other questions? Maybe I can ask a question. You mainly considered uncharged and charged scalar fields. How about when we add a spin, like, for example, when we have a neutrino or an electron?
Right, very good question. So I can tell you about Kerr. So, well, let's go back to Schwarzschild. The construction on Schwarzschild works equally well for fields of all spin. Okay. On Kerr, you have superradiance for all bosonic fields. So what I've said would carry over. So you've got no Hartle-Hawking state for electromagnetism, and I would imagine also for spin 2 for gravity. The electromagnetic case has been looked at. There's papers by Casals et al. I'm not aware of anything doing the quantum gravity case, but that would work through. Oh, there's a recent paper by Zahn where they include spin 2 on Kerr as well. Fermions are different. So fermions do not exhibit classical superradiance. And because fermions satisfy anti-commutation rather than commutation relations, the quantization process is rather, you've actually got rather more freedom in how you define states. So for a fermion field on Kerr, you can define something that looks more like a Hartle-Hawking state. It's not regular everywhere, but it's regular close to the horizon. In terms of charged, so charged fermion on Reissner-Nordstrom, for example, I've just started looking at. So hopefully I will know more in future on that case.
Yes, thank you. One question I would have, what if we would also consider, like, I mean, for neutrinos, we have on one hand the spin, but on the other hand, we have also the oscillations of the mass eigenstates. Do you know or have any intuition what may happen there?
No, I mean, the work that's been done on Kerr is for a massless fermion. In the massive case, I can't, so it is known whether there are, so I guess there aren't any classical instabilities. I'm not sure that introducing a mass for a fermion would really change, at least the qualitative nature of the picture. I would expect it to be broadly similar. Yeah.
Okay. Thank you. Are there any more questions from the audience? If not, I would say we end the official part of the seminar now. Thank you very much again for your very nice talk.